the exact definition of what positive real is for multi-input, multi-output matrices, transfer functions which are matrices, I have not yet given, but the definition is such that it simplifies to exactly the definition that we had. I mean the kind of definition that we had about the Nyquist plot, that kind of definition, or about the right half plane mapping to the first and the fourth quadrant. Well, the same kind of thing does appear, but that I would give just after finishing the proof of this positive real lemma. Okay, so let's finish the proof of the positive real lemma. So okay, so coming back here, so this is what it means, and at this point I would invoke the spectral factorization theorem. Okay, so what does the spectral factorization theorem say? Well, the spectral factorization theorem says the following, that suppose you have US, which is okay, let's assume this US is a P cross P matrix which is positive real. Okay, what we mean by a positive real matrix is something that I have not yet defined, but I will define just after this, after the complete proof of the positive real lemma. But just assume, I mean, you could listen to this portion by just thinking of US as a scalar, single input, single output case, and that would be good enough. So you assume US is a P cross P positive real and Hurwitz, that means stable. Then there exists R cross P matrix, which is an R cross P matrix which is Hurwitz. It is proper rational. So then there exists a R cross P matrix which is Hurwitz proper rational. Let me call it V of S, such that U of S plus U S star transpose is equal to, perhaps I'll just use a new sheet. So we are talking about spectral factorization. So suppose you have a U of S which is a P cross P positive real and Hurwitz matrix. Then there exists an R cross P matrix which is Hurwitz, that means stable, proper rational, and let us call this matrix V of S, such that U of S plus U transpose of minus S is equal to V transpose of minus S times V of S. Okay. So let me explain what is going on here. So we are talking about U of S, which is a P cross P positive real matrix. Positive real, well, I'll give you the definition shortly, but it's a positive real U. So I mean, instead of this P cross P, one could just think of 1 cross 1, and so this is just a transfer function, and it is positive real Hurwitz. Then there exists a R cross P. Well, this R cross P business and the P cross P, this only appears in multi-input, multi-output. In single input, single output, of course, this R will be P is 1 and R will also therefore be 1 cross 1. There exists a matrix which is Hurwitz proper rational, call it V of S, such that this matrix U of S plus U transpose of minus S, the sum of these two matrices is equal to the product of V S with V transpose of minus S. And the R comes in the matrix case essentially because when you add these two matrices, they are P cross P square matrices. It has a certain rank, and that rank is this R, and therefore this matrix V is not really a square matrix, but it is so V is more like this, and so V transpose is like that. Okay, and so the product of these two matrices is a square matrix. So this has P columns and R rows. That is what Vs is. Okay. Now, if you see, earlier we had said Gs is stable, and therefore this thing holds. But you see G of j omega plus G transpose of minus j omega. So if you look at the imaginary axis, you are saying that in the imaginary axis it's positive definite. If you think of this as matrices, it's positive definite matrix. So what would happen is when you look at this sum will have roots which are on the left half plane and roots which are on the right half plane, and then this V transpose minus S times Vs is constructed by using all in this sum, using all the roots which are in the left half plane. You use that to somehow construct this Vs, and then the V transpose minus S comes automatically because of some symmetry which exists in this sum. Okay. Now, the spectral factorization is of course a very well known result and used widely, for example, in communication theory, but we will invoke this. So, because we have started out with this Gs which is stable and has this property, therefore, now we can use this and invoke the spectral factorization theorem, and by invoking the spectral factorization theorem, we can say that G of S plus G transpose of minus S is equal to, okay, let me just continue calling this V transpose minus S into V of S. And now what I am going to do is I am going to start off by looking at state representations of each of these matrices. Okay. So, now if you look at G of S, we have already seen what the state representation of this G of S is. So, it was x dot equal to Ax plus Bu, y equal to Cx plus Du. Okay. Now, if this is the state representation for G of S, then from here we can get the state representation of G transpose of minus S, and the state representation for G transpose of minus S would be, okay, let me call the states here x1. So, x1 dot is going to be minus A transpose x1 plus C transpose U, and y is going to be minus B transpose x1 plus D transpose U. Okay. Now, here we have Gs plus G transpose minus S. So, it is as if these two transfer functions, they are adding up, which is like, so they are two systems which are parallel. I mean, you could think of them as this is G of S, this is G transpose of minus S. Out here you give U, out here you get Y. Okay. So, if you now decide to look at the state representation of the full transfer function that you have on the left hand side, then that is given by x1 dot equal to A0 0 minus A transpose x1 x1 plus what you have here would be B C transpose U, and Y will be given by C minus B transpose x1 plus D transpose U. Yeah. So, what we have got here is the state representation. This is the minimal state, because we have said that this is the minimal state representation for GS. Therefore, this is a minimal state representation for G transpose minus S, and therefore, this is the minimal state representation for what is on the left hand side. So, let me just call this left hand side. So, what we have is a minimal state representation for the left hand side. Now, in the same way, let us consider a minimal state representation for the right hand side. So, in order to construct a state representation for the right hand side, let us assume a state representation for V of S. So, let the state representation of V of S be given in the following way. So, Z dot is equal to, let us say, F Z plus G W, and so W is the input for this V of S, and then okay, let me call it W1, and then W2 is equal to H Z plus J W1. So, if this is the state representation for V of S, then V transpose minus S has a state representation where the matrices involved will be minus F transpose here, and here you will have H transpose, here you will have minus G transpose, and here you will have J transpose. Yeah. But on the left hand side, we were looking at V transpose minus S times Vs. So, this is like saying that W1 is an input to V of S that way, and the output of that is W2, but this W2 is the input to V transpose minus S, and the output to that, let me call it W3. So, it is a series connection if you think about it, and so I will appropriately use W2 as the input for this, for the representation of V transpose minus S. So, the input I will use as W2. Let me call the state, that one I had called Z. So, let me call them Z1. So, Z1 dot equal to minus F transpose Z1 plus H transpose W2, and the output, let me call it W3. So, W3 is equal to minus G transpose Z1 plus J transpose W2. Okay, so now what was there on the right hand side, the net thing, it's a series thing. So, I'll have to put both these state representations together, and I will end up getting a state representation for this thing. And so, the state representation I'll get for this is going to be Z1 dot is equal to, okay, so F0 Z1 plus G W1, okay, and for Z1 dot I will get minus F transpose Z1, and out here I'll get a term because H transpose W2, but W2 is HZ plus Z. So, I would get here H transpose H, and here I would get H transpose J. And the output equation, well, W3 is equal to, I would have minus G transpose. So, this I have taken care of, and then I have J transpose W2. So, putting that in there, I will have J transpose H times Z, and plus J transpose J times W1. So, this now is the minimal state representation for the right hand side. So, if you recall, there was a minimal state representation for the left hand side that of this equation that we obtained, and we have also obtained a minimal state representation of the right hand side of that equation. Okay. And so, this left hand side and the right hand side, ideally if they are equal, that means these two minimal state representations are a similarity transform away. Okay. So, now what we would do is we would use some smart way of manipulating these matrices in such a way that we can show some relation between this and that. Okay. And okay, so one other thing that I wanted to mention is that from the spectral factorization theorem, we get that G transpose S plus G S plus G transpose minus S is equal to this product V transpose minus S V S, and we can always take this V S to be Hurwitz, and if V S is Hurwitz, this matrix F is a Hurwitz matrix. So please remember that this matrix F is a Hurwitz matrix. Okay. So, first what we are going to do is we are going to do a transformation on this second state representation that we got, and the transformation that we would do on this thing is using a matrix which will help us make the system matrix here. We will convert the system matrix here into a diagonal matrix. That means, we will try and get rid of this H transpose H. Okay. Now, the way we get rid of this H transpose H is the following. So, we will use for the transformation a matrix T which is of the form I K 0 I, and this K is not any old K, but this K is a K that would satisfy the Lyapunov equation K F plus F transpose K equal to minus H transpose H. Okay. Now, let me just revisit. This is the equation, the minimal state equation that we got for the right hand side. We want to make this matrix diagonal. In order to make this matrix diagonal, also remember that this F is a Hurwitz matrix. Now, if F is a Hurwitz matrix, this equation for any positive, F is a Hurwitz matrix. If you write down this Lyapunov equation, what you have on the right hand side, well, H transpose H, this is always going to be positive semi-definite. So, with a negative sign, this is going to be negative semi-definite, and therefore, you will always get a solution K for this. Okay. So, this K is the K that you use in the similarity transformation matrix. Okay. So, if you use this K in the similarity transformation matrix, so let us just look at what we would get. We have H transpose H minus F transpose, and we are going to use this. So, I 0 K I, and of course, the inverse of that matrix is I minus K 0 I. So, if you multiply this out, multiply the first two matrices, you get F 0, and this one, when you multiply, you get K times F plus H transpose H, and the other one you get minus F transpose, then post multiplied by I 0 minus K I. Okay, so, when you multiply this, when you multiply this, you get F 0, and then you have this thing multiplying this thing. Now, if you see, what happens is you have K F plus H transpose H plus F transpose K, but that is essentially this Lyapunov equation. So, you get a 0, and then the last one gives you minus F transpose. So, we have effectively managed to diagonalize that matrix by using a similarity transform T. Okay. So, now if you use this T and you diagonalize, then Okay, then the kind of matrices that you would get, what I will do is, rather than do the calculations, I just write down what are the matrices that you would get. See, these were the original matrices that you had, and if you do this transformation using I k 0 I, then the system matrices that you would get are, okay. So what I'll do is I'll write down the original system matrices and I'll write down what the corresponding system matrices are. So the original matrices, this is the system matrix that you had, and under transformation this goes to F 0 0 minus F transpose. Okay. Then you had the input matrix as G H transpose J, and under this similarity transform, under the similarity transform, this will continue to be G, and here you will have K G plus H transpose J. Then you have the other matrix being J transpose the C matrix or the observable matrix to be this, and that will get transformed to J transpose H plus G transpose K, and here you will have minus G transpose will remain as it is, and then the last one, which was J transpose J, the feed through matrix, that will remain J transpose J. Okay. Now, this is the new set of matrices that you have, and what we will now show is that you see the right hand side at these matrices, and one can show that there is a similarity transform that you can do on these matrices such that you get these 4 matrices. Okay. So this is what we are saying. This left hand side matrix, this is the right hand side matrix. There is a similarity transform which will take this matrix to here, this matrix to here, this matrix to here, and this matrix to here. Okay. I am not going to go into the details of how to construct the similarity transform, but I would just say that this similarity transform that you use, you can show that it's a block diagonal matrix and so on. And now it should be clear that once you do this transform, whatever this gets transformed by, so suppose you have that similarity transform acting on this to make it this, then whatever this gets transformed by, this will turn out to be equal to D plus D transpose. So this J transpose J is really, let me pull out the positive real lemma. This last equation says D plus D transpose is equal to W transpose W. This is really saying that this matrix is the same as this matrix. Okay. Now, when you do the other transforms, then from equating whatever is here to whatever gets transformed here, you will get this equation, and the other equation about L transpose L, that you will get from the similarity transform that takes A to F. Okay. So, as a result, what you have shown from this construction is, by this methodology and showing the similarity transform between these two, you have shown that these equations are going to be satisfied. Okay. And so, that was the converse proof of the positive real lemma. Okay. So, it looks like I am out of time, and so let me stop this lecture. But what I would do in the next lecture is, I would start off by giving the definition of positive real for matrices, for the matrix case. We proved the positive real lemma, assuming, I mean, initially I had only given the understanding of what positive realness is for scalar single input single output system, but of course it can be extended to a matrix case. The proof of positive real lemma because the proof was dealing more with state space, it really did not matter whether we were looking at the single input, single output or the multi input, multi output case. But what exactly the definition of positive realness is, that I would talk about in the next lecture.